Hello everyone, welcome to this lecture. In the last few lectures we studied model parameter estimation using curve fitting. Now curve fitting is also known as a phase separation technique because in curve fitting the contributions of different modes to the FRFs and IRFs, right, they are separated mathematically in order to obtain the model parameters of individual modes. So through computational processing the contributions of different modes are separated to identify model parameters of individual modes. In this lecture, we are going to talk about phase resonance testing, which is an alternative approach to model parameter identification. So, what is phase resonance testing? So, the phase resonance testing, also referred to as normal mode testing or appropriated force testing, is the excitation and measurement of the normal modes of a structure. So, the phase resonance testing involves excitation of a structure such that it vibrates in a normal mode, and then measurement of the modal properties of that normal mode is something that we intend to do, right. So, that is phase resonance testing. So, here the structure is excited in individual modes and then the model parameters of individual modes are directly obtained by measurement. So, that is how it is different from the process of curve fitting. Now, what are normal modes of a structure? The undamped modes of vibration of a structure are called the normal modes. In practice, structure has damping, right. So, then how undamped modes are related to a practical structure? So, if you assume that the damping is hypothetically removed from the structure, then what we would have would be a undamped structure, and the modes of that undamped structure are nothing but the undamped modes. So, therefore, we can think about undamped modes of a structure assuming that the damping has been hypothetically removed from the structure. So, the phase resonance testing is about making a structure vibrate in a normal mode and then determining the modal parameters of that mode by direct measurement. So, therefore, this is different than the approach of phase separation technique, right, or the phase separation testing, that is obtaining the modal parameters by curve fitting. So, there what we measure are not directly the modal parameters, what we measure are the frequency response functions or impulse response functions. And then the FRFs or IRFs, they are processed, they are mathematically processed to obtain the model parameters. But in phase resonance testing, we directly measure the model parameters. So, now why it is important to know the normal modes? Does it have any utility? So, now the experimentally identified normal modes, they are useful to validate and if necessary update analytical and numerical models, right. So, the numerical models typically the finite element models are used. So, finite element models generally either are undamped, right, that is damping is not model, or if the damping is model then it is based on a proportional damping model. So, in either of these cases the modes corresponding to the model will be undamped modes, and therefore, if we have knowledge about the normal modes of the structure, that is the undamped modes of the structure, then a direct and consistent comparison between the experimental modes and the modes of the FE model would be possible, right, and that would allow us to do a very reliable validation of the finite element model, right. So, validation of finite element model is very important in aircraft industry, and it is desired that the validation is done in a very reliable and accurate manner because these models then would be used for predicting the aeroelastic response and then predicting the stability limit speed, and therefore, knowledge of experimental normal modes is required for an accurate model validation, right. So, in the curve fitting approach, phase separation approach we studied, that generally yields the complex modes of the structure, and if those modes are to be used for validating an undamped model or a FE model with proportional damping, then we need to realize the complex modes first, and the realization of the complex modes generally involves some approximation. Mode shapes would be distorted to some degree, and that would affect the quality of model validation. So, that is why if the undamped model or an FE model with proportional damping is to be validated, then the real modes of the structure or the normal modes of the structure would be helpful. So, now how to excite normal modes? So, what we do is that we apply harmonic forces of the same frequency on the structure at multiple locations using vibration shakers. So, idea is that we excite the structure with forces at multiple locations and the frequency of all these forces has to be equal, right, so that the structure vibrates with a single frequency. Now, the question arises, what should be the frequency, magnitude and phase of the excitation forces, correct? What should be the frequency of these forces? the frequency will be equal, but what should be their frequency, right? What should be the magnitude of the forces at different locations, and what should be their phase relationship, so that the structure vibrates in a normal mode. So, the frequency of the excitation force should be equal to the undamped natural frequency of the mode to be excited, correct, because we know that the steady state response of the structure will be at the same frequency as the frequency of the excitation forces, and if we want to excite the structure in a normal mode, the frequency of excitation should match with the natural frequency of that mode, correct. So, we therefore must know what that natural frequency is, right, and that frequency should be used for excitation of the structure. So, that is the first condition. Then the forces that are applied, they need to be tuned such that the resulting response is entirely governed by the corresponding normal mode shift. So, therefore, the magnitude and phases of different forces which are applied at different points, right, they should be tuned such that the response that is generated, the steady state response, is in accordance with the corresponding normal mode shape. Okay. So, then the question arises, because we do not know the normal mode shape, how do we ensure that the forces have been tuned such that the only normal mode is excited. So, now we would see that how to obtain the undamped natural frequency and how to obtain the force vector, right, which when applied would ensure that the structure vibrates in the corresponding normal mode, right. We would see some methods for that. So, those methods are based on satisfying a condition which is called as phase resonance condition. So, therefore, now we are going to talk about what is phase resonance condition, because when the phase resonance condition is satisfied, that would ensure that the structure vibrates in a normal mode. So, let us now look at what is phase resonance condition. So, phase resonance condition is the condition for the vibration of a structure in a normal mode. So, the phase resonance condition when satisfied indicates that the structure is vibrating in a normal mode, in an undamped mode of the structure, right. So, now to derive the phase resonance condition, let us look at equations of motion. So, this is the equation of motion for a multi-degree of freedom system in matrix form, which is mx double dot plus cx dot plus kx is equal to f naught e to the power I omega t, and this is the equation of motion for the harmonic vibration of the structure. So, here the forces are applied at different degrees of freedom, and the amplitude of the forces is represented by vector f naught, right, here, and the frequency of the force is omega. So, this is the force vector, right, it is the force vector, and f naught is the amplitude of the force vector. So, what would be the response of the system? That will be the steady state response. The steady state response would be at the same frequency, right, and it can be given by x t is equal to x naught e to the power I omega t. So, this is the steady state response, and the vector x naught is the vector of steady state amplitude, right, at different points. Let us now assume that the vector f naught, which is the vector of the force amplitude at different locations, is a real vector. It is a monophase vector, which means that the force amplitude at different locations, they are in phase or they are out of phase, right. Let us now try to analyze that what happens to the displacement response. So, the steady state response in general would be complex, right, and let that response is written in this form. So, x naught is written as sum of the real part plus I into imaginary part of the response. So, XOR is the real part of the steady state response and XOI is the imaginary part of the response. So, now we substitute x of t in the equation of motion, and in place of x naught we substitute x naught r plus I into XOI, right, and if we simplify we get these two equations, right. So, we get these equations by separating the real and imaginary parts on the left and right hand side and then equating the real and imaginary parts. So, these are the two equations we get. So, now these two equations we are going to further analyze to see what is the state of vibration. So, let us now try to study the state of vibration of the system when the real part of the response is 0, right. So, you can see here we are saying that the real part of the response is 0, and let us try to study that what is the state of vibration of the system if the real part of the response has to be 0. So, let us now look at the second equation we got, right, on the previous slide. So, this is the equation we had, and now let us substitute XOR is equal to 0 in this equation. So, that gives us this equation. So, what does this equation represent? So, this equation basically represents the undamped eigenvalue problem, right, or the eigenvalue problem corresponding to the undamped state of the structure. So, what is the conclusion? So, we see that if the force vector that is being applied is a real force vector, which means it is a monophase vector, and if the real part of the steady state response is 0, right, then the structure would vibrate with its undamped natural frequency, one of its undamped natural frequency, and the steady state response of the structure would be in accordance with the corresponding normal mode shape. That is the interpretation of this conclusion. Conversely, we can also say that if the force vector is monophased, that is real, and if the frequency of the force is equal to the undamped natural frequency, is equal to one of the undamped natural frequencies, then the real part of the response will become 0 and its imaginary part will match the corresponding undamped mode shape. So, that is an alternative interpretation of this equation. So, this effectively excites an undamped mode. So, this lays down what needs to be done in order to excite an undamped mode, right. So, in summary, the vector of force amplitude must be real, the forcing frequency must be equal to the undamped natural frequency of the normal mode that is to be excited. When these two things are done, right, and when it is ensured that the real part of the response is also 0, then the structure would vibrate with the normal mode shape. Let us now try to analyze the first equation we got, right. So, this is the equation we had, and now let us see if we make x naught r 0, then we get this equation. So, what does this equation represents? If we see on the left hand side, what we have got is the vector of damping forces. So, minus omega c into the imaginary part of the response, right. This makes up the forces due to damping, right, at different locations, and therefore, under this condition what is happening is that the damping forces, they are countering the external forces acting on the structure. So, when the vector f naught is real, it is monophase, when the real part of the response is 0 and the frequency of the force is equal to one of the undamped natural frequency, then the damping forces in the structure would balance the external forces being applied. And then what would happen? The inertia forces will be completely balanced by the elastic forces, the forces due to stiffness, correct, and that is condition for excitation of a normal mode, right. So, when an undamped mode of vibration occurs, what is true is that the inertia forces are completely balanced by the forces due to elasticity. So, therefore, this also demonstrates that the structure is going to vibrate with a normal mode, because the damping forces alone take care of all the external forces, right, which ensures that the inertia forces, they balance the stiffness forces or the elastic forces. So, what would be the response of the system? The response would be xt, and since the XOR is 0, xt is simply equal to I times XOI e to the power I omega t, correct. So, the response is purely imaginary, which means that it is at a phase angle of 90 degree with the force vector. So, therefore, the total response vector is in quadrature or at 90 degree with the force vector. Thus, the response at all the degrees of freedom, they are at 90 degree with the forces at those degrees of freedom. So, and since the force vector is monophase, the response vector also becomes monophase, right, and the phase angle between the monophase excitation vector or the force vector and the monophase response vector is 90 degree, and this is called phase resonance condition. So, what is phase resonance condition? If a monophase excitation vector is used to excite the structure, right, at certain frequency, then the phase resonance condition is satisfied when the responses at all the points, they are at 90 degree with the forces at those points, right. So, that is the phase resonance condition, and this condition is true for any distribution of damping, because you see in this analysis we did not assume whether the damping is proportional or non-proportional. So, this phase resonance condition will have to be satisfied for excitation of a normal mode, irrespective of whether the damping is proportional or non-proportional, and we analyze this using in the case of viscous damping, but this condition can also be proved for the case of system with structural damping. So, now let us try to see that how to obtain the force vector for excitation of normal modes. we have developed or we have derived the phase resonance condition, which when satisfied guarantees excitation of a normal mode. But how to obtain the force vector which needs to be applied so that the structure vibrates in a normal mode and it satisfies the phase resonance condition. So therefore, what we need to do is that we need to apply a specific pattern of the excitation forces, right, called an appropriated force vector at a frequency equal to the undamped natural frequency of that mode, right, to set the normal mode. But then what should be this specific pattern of excitation forces? So one may argue that we just got the relationship of the force F naught in terms of the damping matrix, like we got the relationship that vector F naught is equal to minus omega into C into the imaginary part of the response. So if we have a mathematical model of the structure, right, then we should be able to find out the force vector that needs to be applied, because if the mathematical model is known, we also would know the undamped natural frequency. So can we not excite the structure using that estimate of the force vector? There are two problems with this approach, right. The first is that our objective of finding model parameters of normal mode is to validate the mathematical model. So if we want to validate the mathematical model, we cannot use the mathematical model itself for computing the properties of the normal mode, right. Secondly, the mathematical model in general will not give an accurate estimate of the undamped natural frequency and a force vector, because in general it may have some inaccuracies with respect to the experimental structure, and therefore those estimates will not be accurate enough for excitation of the normal mode. So therefore what we want is a method which is based on experimental measurements, okay. So we would like to find the force vector needed for excitation of a normal mode through experimental measurements, right. So we note that the force vector for excitation of normal mode, it can be related to the FRF matrix, right. Such a vector can be found from the FRF matrix, and because FRF matrix can be measured, then we can estimate the force vector that is needed for excitation of a normal mode from the measured FRF matrix. So now for a real force amplitude vector, right, when the force vector that is being applied, if it is real, it is monophase, then the real part of the response will depend on the real part of the FRF matrix, because the FRF matrix is in general complex, it has real part as well as imaginary part, and if the force vector that is being applied is real, then the response, the real part of the response will depend only on the real part of the FRF matrix, right, and the imaginary part of the response will depend only on the imaginary part of the FRF matrix, and that is why we can write the real part of the response as the real part of the FRF matrix times the force vector amplitude. So therefore XOR is equal to alpha r into F naught O. So XOR is the real part of the response and alpha r is the real part of the FRF matrix. And now we just saw that for phase resonance condition, the real part of the response should be 0 when the force vector is real, right. So therefore for phase resonance XOR should be 0. So when the real part of the response is 0, the equation we get would be that alpha r into F naught should be equal to 0. So this is the fundamental equation based on which the force vector can be estimated. Let us now look at how to find the force vector for excitation of normal modes, and let us first look at what is referred as Asher's method. So we saw that the fundamental relationship that should be satisfied for the excitation of normal mode is that the real part of FRF matrix multiplied by the force vector should be equal to 0, correct. So when the normal mode is excited, then this relationship would be satisfied, and when the normal mode is not excited, this relationship would not be satisfied. So therefore for satisfaction of this relationship, the determinant of the FRF matrix should be 0, because the equations are homogeneous. So a solution to these equations can exist only when the determinant of the FRF matrix is 0, correct. So therefore the determinant of alpha r should be equal to 0, right. So if we have the measured FRF matrix, right, so then we will have a certain frequency range over which those FRFs would be available. So what we can do is that we can, for each frequency, discrete frequency in the frequency range, we can find the determinant of the real part of the FRF matrix and check whether it is equal to 0 or not. So the frequency at which, the frequency omega at which the determinant of the real part of the FRF matrix is 0, that frequency would be the estimate of the undamped natural frequency of the structure, right. So in this way we can find the undamped natural frequency. We can find the determinant of the real part of the FRF matrix over the whole frequency range, and all those frequencies at which this determinant is 0 indicate the undamped natural frequencies of the structure. So once undamped natural frequencies have been found, what we can do? Now we can substitute the undamped natural frequency in the fundamental relation, right, to obtain the force vector. So let us say that the undamped natural frequency is represented by omega ur. Okay. So you can see this is the omega ur is the undamped natural frequency. So the subscript u is used to represent the association with the undamped mode. So let us say the corresponding force vector is f naught ur, the force vector which would ensure excitation of the structure at so this is the force vector which would ensure excitation of the structure in the corresponding normal mode. So this equation is now written at the undamped natural frequency. So you can see this is the real part of the FRF matrix at undamped natural frequency which has been estimated, and now these are homogeneous equations, and now we can solve these equations for f naught ur, right. So because equations are homogeneous, the estimate of f naught ur will have a scaling factor, an arbitrary scaling factor. So to solve these equations, one of the elements of the f naught will have to be arbitrarily chosen, and then the remaining elements can be determined. So that effectively will give us the force vector which will excite the rth normal mode. But now the problem is that the measured FRF matrix is in general rectangular, correct. So when we measure FRFs, generally the excitation coordinates, the number of excitation degrees of freedom are far less than the number of response degrees of freedom, isn't it. So therefore the FRF matrix we get in general is a rectangular FRF matrix, and the equation that determinant of the real part of the FRF matrix should be 0 cannot be used, right, because that requires a square FRF matrix. Now we are going to look at couple of methods which allow use of rectangular FRF matrix in order to determine the undamped natural frequencies and the corresponding appropriated force vectors. So this method defines what is called as real mode indicator function, RMIF. If the response is monophase, then the real part of the response can be written as lambda times the imaginary part of the response. So here lambda is a real scalar quantity, right. So now our objective would be to determine those values of frequency omega for which the response is monophase, right. So in order to determine those frequencies, an objective function is defined in this method, right, the objective function j, which is the square of the norm of the difference vector, that is XOR minus lambda XOI. So therefore this difference has to be reduced in order to obtain the frequencies which would ensure a monophase response. So this j can be written using transpose notation like this, okay, XOR minus lambda XOI transpose into XOR minus lambda XOI, right. And now the condition for minimum of j is that the first derivative of j with respect to lambda should be 0. So this is the result of application of this condition, and now we know that the XOR and XOI can be written in terms of the real and imaginary part of the FRF matrix. So we can substitute those relations here, and if we simplify we get this equation, right. So this is what we get after substituting XOR and XOI in terms of the real and imaginary part of the FRF matrix, because we saw that XOR is nothing but alpha r into f naught and XOI is nothing but alpha I into f naught, okay. So this is the equation we get. So this represents an eigenvalue problem, right, where lambda is the eigenvalue and f naught is the eigenvector, correct. So this represents an eigenvalue problem in lambda and f naught, and because the matrices alpha I and alpha r, they depend on the frequency omega. So that is why these eigenvalues and eigenvectors would change with the excitation frequency omega. So in this method what we do is that we solve this eigenvalue problem, and we determine those frequencies for which the eigenvalue is 0. So we determine those frequencies for which the eigenvalue is 0, because when the frequency changes the eigenvalues changes, and for some frequencies the eigenvalues may become 0. So those 0 eigenvalues represent a monophase response, because we can see that when lambda is 0 then XOR would become 0, correct, and that would satisfy the phase resonance condition. So, therefore, the plot of eigenvalues, different eigenvalues which are obtained from solving this eigenvalue problem as a function of omega, that plot is referred as real mode indicator function. So, we solve the generalized eigenvalue problem at each frequency omega, and then the monophase response corresponding to lambda is equal to 0 satisfies the phase resonance condition and hence represents a normal mode. So, we plot the eigenvalues as a function of omega, and wherever those plots cross the 0 line, that represents the undamped natural frequency, and the corresponding eigenvectors corresponding to those frequencies represent the force vectors which are needed to excite the normal modes. Now, for a typical system, this plot of real mode indicator function is shown here. So, you can see this system has 3 undamped natural frequencies, and you can see there are 3 eigenvalues corresponding to this eigenvalue problem, and when they are plotted and wherever they cross the 0 lines, those are the undamped natural frequencies. So, these red dots here, they represent undamped natural frequency. So, therefore, this is the undamped natural frequency 1, this is second undamped natural frequency, and this is the third undamped natural frequency, and the corresponding eigenvectors are the force vectors which are needed to excite the normal modes. Let us look at another method. This method defines what is called as multivariate mode indicator function. So, this method defines an objective function, right, which is the ratio of the norm of the real part of the response and the norm of the total response, okay. And then we can write the numerator and denominator using transpose notation, and then we can now substitute the real part and imaginary part of the response using the real and imaginary part of the frequency response function matrix. After simplifying, we get this result. So, this again you see it is in the form of an eigenvalue problem. This again is in the form of an eigenvalue problem in terms of these matrices, like this is one matrix here, and then we have this is another matrix. So, this is an eigenvalue problem in terms of these two matrices, and lambda is the eigenvalue and f naught is the eigenvector, correct. So, here we solve the eigenvalue problem at each frequency, and the excitation frequencies corresponding to the local minimum values of lambda are the undamped natural frequencies. So, because you can see when the lambda is minimized, then the and ideally if the lambda becomes 0, the numerator of this expression would be 0. So, the minimum value of lambda corresponds to the excitation of the normal mode. It corresponds to the undamped natural frequency, because ideally if lambda is 0, then XOR would be 0, and that would ensure the satisfaction of the phase resonance condition, and then the normal mode would be excited. So, therefore, what we do in this method, at each frequency we determine what is the lowest eigenvalue, and then we plot the lowest eigenvalue at each frequency as a function of omega, and that plot is called multivariate mode indicator function. So, once we determine the frequencies corresponding to the local minimum of the eigenvalues, the corresponding eigenvectors would be the corresponding force appropriated vectors, the force vectors to excite the corresponding normal modes. So, this is a plot of multivariate mode indicator function for a typical system. So, you can see here the lowest eigenvalue at each frequency has been plotted as a function of frequency. So, there are 3 local minima. You can see this is the first local minima. So, corresponding excitation frequency is the undamped natural frequency. This is the second and this is the third, and the corresponding frequencies are the undamped natural frequencies. So, the RMIF and MMIF removes the difficulty with the Asher's method. Okay. Here the rectangular FRF matrix can be used to set these eigenvalue problems and then find the eigenvalues and eigenvectors to plot these mode indicator functions, from which the undamped natural frequencies and the force appropriated vectors can be determined. So, this multivariate mode indicator function can also detect the existence of repeated roots or repeated poles. For that, the other eigenvalues can also be plotted, and the local minimas in those plot of other eigenvalues will indicate repeated roots or repeated undamped natural frequencies. So, let us now look at the basic steps in performing phase resonance testing. So, the first step is that we have to decide the number of response transistors and exciters and their locations. So, at least 2 exciters are required, If more exciters are there, that would help to satisfy the phase resonance condition in a better way and then exciting the normal mode, right. Then we measure all the FRFs between the response and excitation DOF. So, we measure the FRFs corresponding to all combinations of response and excitation DOFs. Then using one of the methods we studied, we determine the estimate of the undamped natural frequencies and the corresponding force appropriation vectors. Because once the FRF matrix is known, we can use one of the methods we studied like RMIF or MMIIF or some other method, to find the undamped natural frequency and the corresponding force appropriation vectors. Now, if let us say we want to excite the RF normal mode. So, then what we do? We apply the corresponding estimated force appropriation vector at the estimated undamped natural frequency of the mode. But in practice, we may have to tune these force amplitudes at different points, okay, and the frequency to ensure that the phase resonance condition is indeed satisfied, because the FRF matrix that has been measured may have some noise and maybe there may be some inaccuracies. So, that will affect the estimated undamped natural frequencies and the force appropriation vectors. So, therefore, the phase resonance condition may not be completely satisfied with that data, right, and therefore, in practice the frequency of the force and the force amplitude and the phase between them may have to be little bit tuned and adjusted to ensure that the phase resonance condition is satisfied. So, once the RF normal mode is excited, the responses are measured, and the responses would now correspond to the corresponding normal mode shape, and therefore, to obtain the mode shape we measure the responses at all degrees of freedom, and they would constitute the RF normal mode. Now, to obtain the corresponding damping factor, we remove the appropriated force vector and measure the resulting free decay response, and from the free decay response we determine the modal damping factor. So, in this way we obtain the estimate of the undamped natural frequency, the corresponding normal mode shape and the damping factor of the mode, right, through phase resonance testing. In this way we come to the end of this lecture. In this lecture we studied what is phase resonance testing, how it is different from phase separation technique or curve fitting, right, and how the structure is excited in a normal mode and how the modal parameters of the normal mode are measured. We stop here now. Thank you.